great. What are you doing just now?
You know what? I just follow Elon Musk on Instagram.
Who's that?
He is a very, very great man. He also a super engineer.
What does he invent?
He has invented a electric car.
Yeah, that's great.
Oh, that's when you know about him?
Yes, actually I know.
Did you know, Shah? He also invented a rocket.
Oh, I don't know about that.
Yeah, we actually can go to space.
Did you know they are the great men from the other century?
No, I don't. Please share with me.
The guy that I want to share with you is Heinrich Lenz.
Oh, who's that?
He is the one who proposed the idea of the relation between magnetic and electric.
Wow, that sounds great. Tell me more.
I think we should figure it out more after this.
Let's see.
Yeah.
Thank you for the splendid introduction. Assalamualaikum warahmatullahi wabarakatuh and hello everyone. My name is Hairul Faizi bin Hairulnizam and my matrix number is 200942. For my part, it will split up into two main things, which are the short biography of our scientists and the brief of Lenz Law. For the first point, which is the short biography, this is our scientist. His name is Heinrich Friedrich Emil Lenz. He born on 12 February 1804. He is a physicist of Baltic German descent. He born in Dorpat, or now known as Estonia, on 1804. Estonia is a country in European continental. He studied chemistry and physics at the University of Dorpat. He published a memoirs of St. Petersburg Academy of Sciences after a voyage. For your information, a voyage is an act of traveling around the world on a ship. So when he at the sea, he learned something and get an idea, so he published the memoirs. He studied electromagnetism in 1831. In 1839, Lenz produced several medallions using electrotyping. This is medallion example and the process of electrotyping. He became director in the year of 1863 to 1865. Before that, he taught at Petrishul in the year of 1830, and after that at an artillery academy. Before he became a director, he served as the Dean of Mathematics and Physics at University of St. Petersburg, Russia, from the year of 1840 to 1863. He died in Rome after suffering from stroke on 1865. So this is a summary of his short biography of Lenz Law. We can see that he born on 1804 and he died at 1865. Moving on to our next part, which is what is Lenz Law? Lenz Law can be defined as an induced electric current that always flows in a direction such it opposes the change which produces it. So for an example for this law, we can see this experiment, but I will not explain about this experiment because this part will be covered by Mr. Lok Yu Sheng. So from this four picture, we can see it needs a coil and a magnet to perform Lenz law. So moving on to the formula of Lenz law, we can see that the induced EMF is produced when the change induced EMF is produced from the product of change in magnetic flux with the number of turns in coil in a negative sign, why there is a negative sign? This is because Lenz law is based on Faraday's law of induction. Faraday's law tells us that a changing magnetic field will induce a current in a conductor. Lenz law tells us the direction of this induced current, which opposes the initial changing magnetic field which produces it. This is signified in the formula for Faraday's law by the negative sign. So we can see that Faraday's and Lenz law is quite similar, but the difference is at this negative sign, which was introduced by Lenz law from his finding that the induced current is opposed the initial changing magnetic field. So without further ado, that's all from me about the biography and a short brief of Lenz law. So thank you. I will pass this presentation to Mr. Lok Yu Sheng.
Okay, hello everyone. I'm your professor today. My name is Lok Yu Sheng and my matrix number is 200631. Today I'm going to talk about and explain to you the theory of Lenz law. Okay. Lenz law states that the current induced in a circuit due to a change in the magnetic field is directed to oppose the change in flux and to exert a mechanical force which opposes the motion. What it means is that the current induced in this current carrying loop is depending on the direction of the magnetic field in this magnet and the changes of the magnetic flux. Moreover, we can see that the Lenz law is indicating the negative sign in this formula, which is the Faraday's law of induction. Here are the 4 examples for you to get more understanding about theory of Lenz law. In this first example, we can see that a north pole magnet is approaching to this current carrying loop. And as we all know, the magnetic field of a magnet is going outwards from north to south. Therefore, we can say that the magnetic direction of the magnetic field in this magnet is going to the right. And since the magnet is approaching to this circuit, we can also say that the magnetic flux of this magnet is increasing. The key word for us to determine the direction of the induced current is actually opposed to change, which I have said before. The current is induced in such way that its magnetic field is opposing to change of the magnetic flux of the magnet, which in this scenario is increasing. Therefore, the direction of the magnetic field is actually going to the left, which is opposite the direction of the magnetic field of this magnet. By doing so, the magnetic flux of the magnet is decreased. And by using right hand rules, we can determine that the direction of the induced current is going inwards to the circuit, which in this scenario is anti-clockwise. For the second example as well, the direction of the magnetic field is going to the right, but in this scenario the magnetic flux decreases as the magnet is going away from the circuit. Therefore, in order to oppose the change of the magnetic flux, the magnetic field is induced in such way that it increases back the magnetic flux, which in this scenario is going to the right, which is the same direction of the magnetic field of the magnet. By using right hand rules again, we can determine that the direction of the current is going upwards from the circuit, which in this scenario is a clockwise direction. Then for the third example, a south pole magnet is approaching to the current carrying loop. As we all know, the magnetic field is going out from the north to south. Therefore, we can say that in this scenario, the direction of the magnetic field is going to the left. And since the magnet is approaching to the circuit, we can say that the magnetic flux is increasing as well. In order to oppose the change of the magnetic flux, which is increasing, the direction of the magnetic field is induced into the right side in order to decrease the magnetic flux. In this and by using right hand rules again, in this scenario, it is a clockwise circuit. And last but not least, as the magnetic direction of the magnetic field is going to the left and the magnetic flux is also decreasing, we can say that the direction of the magnetic field is to the left in order to increase and which is the same direction to the magnetic field in order to increase the magnetic flux. In this scenario, it is an anti-clockwise direction. By explaining these 4 examples, I hope that you guys can understand more about the theory of Lenz Law and eventually apply to use for our application as well. Okay, and I hope that my assistant Khairul Azri will explain to you about the example of the Lenz Law. And that's all for me. Thank you very much.
Hello, hi. Thank you, Yu Sheng. My name is Muhammad Azri bin Annuar, and my matric number is 190183. I will explain about the example that relate with the Lenz Law. First of all, as we can see, the conducting wire with the U shape. At the end, we have the resistor, the bar that can move across the wire left and right. The magnetic field of the loop that into the board is 0.8 Tesla, and going to move the bar to the right with the velocity 2 meter per second. The length of the bar is 1.2 meter. We will find the EMF induced current and the direction of the induced current. For the EMF, we can see after we find the equation of the EMF and we simplify the equation, we will get the negative magnetic field times the length of the bar times with the velocity, which is the rate of length change of width with respect to time. We will get negative 1.92 volt. The sign of minus sign to indicate the creation of EMF, that the current is opposition to the change of the flux that cause the reverse of the current. After that, we will find the induced current, which is for the relate from the Ohm's law. After we plug in the value negative 1.92 volt over 5, we will get the induced current, which is negative 0.348 ampere. The negative sign is also the same, which is going to opposite direction of the magnetic field. For the direction of the induced current, Lenz law, it shows that the flux will increase when the area is increased and will cause the induced current to oppose the change. So the magnetic field will point out of the board because the flux is increased. With using our right hand rule, the induced current will flow counterclockwise. That's all from.
Hello everyone, my name is Dineswaran Murugan and my matrix number is 202600. Today we are going to discuss about the applications of Lenz law. Let's go! So the first application we are going to discuss is induction cooker. So before we go into the application of the induction cooker, first of all, we have to understand the basic concept of induction heating. Induction heating is a direct application of law of physics, which is the Lenz law. When immersed in a variable magnetic field generated by an induction coil or inductor, any substance that conducts electricity carries the electrical current induced, also called as Foucault current or also known as eddy current. According to the Joule effect, the movement of the electrons creating these currents dissipates the heat in the substance where they get generated. This video shows an example how the induction heating works. We can see that the steel gets heated when the steel is inserted around the coil. We will discuss this in the next part, where we will discuss about the working principle of the induction cooker. So now, let's move on to the working principle of an induction cooker. The figure 1 shows an example of an induction cooker and the figure 2 shows a dismantled induction cooker. Note the large solenoid at the center. In an induction cooker, the change in magnetic field is produced by a high frequency AC current flowing in a solenoid. An AC current produces a changing magnetic field in a solenoid. The field strength is enhanced by the presence of a soft iron core inside the solenoid. When a coil is placed around the iron core, a constantly changing magnetic flux is produced, and an AC current is induced in the coil. Due to its electrical resistance, the coil is heated by the induced current. Since the electrical resistance of steel is low, large eddy currents are induced and the coil is heated by the induced current. We can detect the current using a multimeter and measure the increase in temperature using a thermocouple.
My name is Kishan Kumar and my matrix number is 202744. I would like to explain about the second Lenz law application in real life, which are magnetic brakes and its working principle.
We need to understand how kinetic energy is transformed into electrical energy using Lenz law and electromagnetic induction. So we know that magnets have their own magnetic field, and when this magnet is moved into a coil, the kinetic energy exists in the movement of magnet. So this kinetic energy is then transformed into electrical energy, which then creates an induced current in the coil. So the electric current in the coil also produces a magnetic field. So the magnetic field opposes the direction of magnet's motion. So based on the picture there, we know that when the magnet is going downwards, the magnetic field is going to oppose it upwards, and hence we know that the magnet is going to move slow. This video demonstrates the magnetic braking using copper pendulum. So the pendulum swings freely when the magnets are not switched on. Once the magnets are switched on, the pendulum experiences a changing magnetic field as it swings, and this induces a voltage in the pendulum, which creates eddy currents, and these eddy currents create a magnetic field that slows down the pendulum and it stops eventually. These magnetic braking are often used in drop tower rides. The catch car brings up the gondolas to the top of the tower, and when given all clear, the latches are disengaged to release the vehicle. After a free fall, the gondolas are brought to a safe and controlled stop by a magnetic braking system. These are much more important now. So at bottom, there are two rows of inert metal plates that run parallel to each set of rails, and these align with permanent rare earth magnets that are mounted to the right vehicle. Each gondola has 4 stripes of magnet, and they are arranged in pairs to create 2 thin gaps that are just wide enough for the plates to pass through. So we know when a gondola drops down the tower, the moving magnetic field induces a closed loop of electric current in the plates called eddy currents, and these generate their own temporary magnetic field that oppose the motion of the permanent magnets. The result is a magnetic drag force that acts on the gondola opposite to its direction of motion, which is similar to a repulsive force within 2 magnets of similar pole. The magnitude of the drag force is directly proportional to the amount of current flowing through the plates, since this determines the strength of the opposing magnetic field, and the amount of current is proportional to speed of vehicle. So this relationship tells us that the braking force will be highest when the permanent magnet just begin to pass over the plate, and the force will decrease linearly as the gondola loses speed, thus providing a smooth non-linear deceleration.
Wow, that was a great video, right? I learned a lot of things from there. How about you, Anis?
Yeah, from my point of view, electromagnetism gives a huge impact.
We can conclude that we learned so much from Lenz Law, and he is a great man from the other century that helped our technologies in this world.
Yeah, see you later.
Bye.